Welcome. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to this, our public lecture series presented by BMO Financial. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone this evening, both those of you here in the live studio audience in the theater and those of you watching online. The lecture itself will last approximately 1 hour and will be followed by a question and answer session. Dr. Kelly Foyle and a team of PI researchers are behind their keyboards for those of you watching online to engage in conversation and questions about the lecture throughout and after. And also, if you have questions, send them in via Twitter or the Facebook feeds. Use hashtag PILive, and we'll see if we can ask some of them to our guest lecturer at the end as well. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. Janna Levin. Dr. Janna Levin is a professor of physics and astronomy at Barnard College at Columbia University. Her scientific research concerns the early universe, chaos theory, and black holes. She holds a BA in physics and astronomy from Barnard College with a concentration in philosophy, and a PhD in physics from MIT. She worked at the Center for Particle Astrophysics at the University of California, Berkeley, before moving to the UK, where she worked at Cambridge University in the Department of Applied Mathematics and Theoretical Physics. Just before returning to New York, she was the first scientist in residence at the Ruskin School for Fine Art and Drawing at Oxford, with an award from the National Endowment for Science, Technology, and Arts. She is the author of a popular science book, How the Universe Got Its Spots, a diary of a finite time in a finite space, and her second book, a novel, A Madam Dreams of Turing Machines, won the Penn Bingham Fellowship for Writers, and it honors exceptionally talented fiction writer whose debut work represents distinguished literary achievement. Fantastic stuff. It was also the runner-up for the Penn Hemingway Award for a distinguished book of first fiction. Her third book, Black Hole Blues and Other Songs from Outer Space, is the basis of her lecture tonight as she discusses the discovery of gravity waves. Ladies and gentlemen, please welcome Dr. Janna Levin.
Thank you. Thank you so much. It's so nice to be here. I spent all day actually calculating alone in an office. It was the most work I've gotten done in weeks. So it was lovely to be here. This is such an inspiring place. And so it really is an honor to be invited. When I started to write this book, I wasn't sure how LIGO, an obscure experiment which physicists knew about, but a lot of people in the general public had never heard of, how LIGO would feature in the book. I actually set out to write a very different kind of book. This is maybe 2013, 2012, something like that. And as a scientist, we were very motivated by this experiment, even though it hadn't reached the public eye, thinking about black holes and how black holes might be detected out in the universe. And as I got into my research for thinking about writing about a campaign, really a struggle to do something creative and risky in the sciences, I became completely enamored of this particular experiment. Actually, after the book was finished, something remarkable happened, which was this experiment actually succeeded. This experiment set out to detect gravitational waves, and we'll talk about that tonight. How many people heard this announcement in around February 2016? It took the entire world kind of by storm, as they say. There was a pause where there were every magazine cover, every newspaper cover, every radio outlet. I was on air in Qatar. I don't know what was happening to discuss this announcement, the announcement of the first direct recording of a gravitational wave from the collision of two black holes 1.3 billion years ago. How many people heard about the announcement? It was exciting, right? It was really exciting. How many people felt like they understood what they were talking about an hour later? Yeah, okay. So this is going to be our job tonight. We're going to spend the time trying to understand the following detection. We're going to listen to it. That's already peculiar. Okay, so let's listen to what the recording was. We're hearing it twice. And then increased pitch. This is the recording, and then it's increased. The pitch is increased because it's easier for the human ear to hear it. Okay, so what the hell is that about? Okay. So we're going to spend the rest of the lecture trying to figure out why this announcement was so huge, why it was so significant, and what it means to record a sound from space. How many of you are science fiction buffs and know that you cannot hear someone scream in space? Okay, more hands than understood the LIGO result. Excellent. So what we're going to discuss is why it's a sound and why it's different. And to do that, we're going to begin in our own backyard, which is the Milky Way. This is an image of the Milky Way galaxy. Now, we cannot travel outside of our galaxy. We are nowhere near capable of doing that technologically. But this is also not a cartoon. This is assembled from real data, genuine observations of the universe. Nothing in here is made up or painted or fake. It's all placed to the best of our understanding where it is located in the universe. And we collect this information about where things are located by collecting light. Right? This is the program Galileo sent us on hundreds of years ago by pointing a telescope at the sky. If you think about it, what Galileo was looking for in the beginning were just sunspots. Our local neighborhood, our closest stellar object. He was looking at Saturn and some other things in our planetary system. He hadn't conceived of the fact that we are a tiny solar system floating in this enormous galaxy of hundreds of billions of stars. There are hundreds of billions of stars in our own Milky Way galaxy. It's some hundreds of thousands of light years across. And yet, even though we are bound to this little rock, third rock from the sun, we can reconstruct in this great detail our own galaxy. The furthest probe we've ever sent into space, Voyager, only recently, past couple of years, broke out of the sun's magnetic influence and went interstellar. You know, we really are bound to where we are. And so if you think about what we know about the universe, it's this gift of being able to collect light brought to us from stars and quasars and objects. Galileo hadn't even imagined other galaxies, and to see both into space and back into the past as we look at the universe the way it was when the light first was sent to us. This is the Sloan Digital Sky Survey. Every object in this astronomical observation, this is real data, again, these aren't cartoons, every object is itself an entire galaxy. Okay. There are as many galaxies in our observable universe, just the part we can see, not even the whole universe, just the part we can see. There are as many galaxies in that observable universe as there are stars in the Milky Way, hundreds of billions. So each one of these galaxies has hundreds of billions of stars or more, maybe some less, but we're pretty average, you know, as things go, the Milky Way. And again, we see all the way out into the great distance. We can see all the way back the light that originated in the origin of the universe itself 13.8 billion years ago. And as spectacular as this portrait is of the entire universe, most of what inhabits our cosmos is actually dark. We know that the universe is made up mostly of a kind of matter we don't know how to identify that does not send light to us. It's called dark matter because we don't know what else to call it. The universe's evolution is driven by a kind of energy we call dark energy because we don't know what else to call it. It's just a proxy. We also know that there are dark things that we can detect indirectly. We know that 1% of all of these stars that we're looking at, the hundreds of billions of stars and the hundreds of billions of galaxies, will be, we don't care about the credits, do we? People slaved away on that. We don't care. 1% of those will become black holes. So here's a portrait of a black hole. Right? This is what a black hole looks like. A black hole. This is not a cartoon. It's a pretty accurate representation. We know there are black holes out there in the universe. We see them indirectly, but there are many, many, many more than we can see indirectly that are simply dark. And so here our story really begins. How do we imagine to probe the universe in something other than light, other than collecting electromagnetic radiation? What else can we do to observe the universe if so much of it is dark? And I'm just going to mention, before we begin to discuss the role of gravitational waves in that conversation, I'm going to mention how we do see black holes. So this is just one of the many examples of evidence, very strong evidence for a black hole. This is a distant elliptical galaxy. And when we look at it in a different waveband of light, we see these enormous jets emanating from the galaxy. They far exceed the entire stretch of the galaxy, millions of light years across. We think that there's a supermassive black hole 4 billion times the mass of the sun in the center of this galaxy, like an anchor in its core. And that galaxy is churning up electromagnetic fields. So even though the black hole itself is dark, it is twisting up everything around it so dramatically that it's creating these very powerful jets. And so we indirectly see lots of evidence for black holes. That's just one example. And again, that was real data, real observations. But let's try to figure out, how would we detect black holes if they were just sitting there by themselves against the dark backdrop of space? How would we see black holes when they're genuinely dark? And to do that, we have to think about gravity, because black holes are a form of pure gravity. And here enters Einstein. You know, who doesn't love Einstein? This entire institute is basically based on Einstein's theory from 1905 forward. Einstein begins to think about gravity, and what he wants to do is he wants to get rid of everything else that's in the way. So right when we think about the effects of gravity on our ordinary daily lives, we think of feeling heavy, right, or fighting against it. You might feel heavy in your chairs, or you might feel heavy in your feet. We could do this thought experiment of imagining we were standing in an elevator cab, feeling heavy on our feet. Einstein didn't like any of these examples because he thought, what does an elevator have to do with it, or a chair, or a floor? What are these things doing in this conversation about gravity? Why don't I get rid of them? So he imagines you cut the cable of the elevator. Imagine you've woken up in an elevator cab that is free falling. It's been cut from a very long tower. I'm not going to ask why you're waking up in an elevator. It's not my business. But you wake up in the elevator. Maybe there's no windows. You're just in this black box. You would have no way of distinguishing between whether you were floating in empty space or you were floating the way the astronauts do in the International Space Station, or if you were falling in an elevator. You would literally feel weightless. If I had this clicker with me in this free fall experience, and I let the clicker drop it in front of me, it would look like it was floating. I could pour water and drink it from the air the way the astronauts do. I would feel as though I was completely weightless. Einstein called this the happiest thought of his life. He knew it was the key insight right before his next step. Before we take the next step, let's just remember, gravity is about falling. Gravity is about weightlessness. And to give you a demonstration of that, I'm going to show you this again, real video of these artists from London. Jem Finer on the right, if any of you used to be into punk rock, he used to be in the Pogues. Ansuman Biswat on the left, another British artist. And they're in one of these vomit comets. One of these rocket flights, these parabolic rocket flights, if you've ever heard of them. What these flights do is they go up for a while. They're not in outer space. They're just planes. They're not wearing spacesuits. They're just planes. And then, this is the phase that they're in, the plane drops, free falls, nosedives, just drops out of the sky. And during the fall, these are like the guys in the elevator cab. They might as well be in the International Space Station. They're floating in empty space. These cosmonauts who spent most of their lives training to go to space are now cursing the collapse of the Soviet Union when they have to throw around these artists. Eventually, they actually do get onto carpets. And they float on the carpets for a while. And then this goes on. Now, there's an unhappy ending to this story, right? Which is if it continues to fall and crashes into the crust of the Earth. So they don't want that to happen. And you'll see it's starting to happen a little bit now. You can kind of tell the plane's going to scoop up. And as it scoops up, it'll accelerate faster and faster until it pushes the air. That's what they're feeling when they're kicking like that. They're feeling the pressure of the air coming up, and the plane pins them to the floor, and they feel that conventional sense of heaviness on the floor again. But I want you to think about, in this example, is not that gravity is making them feel heavy. It's that the plane, by stopping their fall and getting in the way, is making them feel heavy. What gravity does is actually makes them feel weightless. This is another pretty spectacular video. I'm not going to show the whole thing in case I get into copyright trouble. This is the band OK Go, and they're in a parabolic flight. Sorry, AV guys, I'm fighting with you over the volume. You can go ahead and control the volume, sorry. Okay, so they're about to go into the flight. Oh, but don't kill the volume. Okay, here we go. They're falling, the plane is falling, and they're just going to take advantage of the fact that they're completely weightless and in free fall. It's pretty spectacular. There's no wires. This is all for real. Apparently, there was a lot of vomit on the Vomit Comet. They did like 52 takes before they got it right. Okay. It's pretty great. We won't show the rest of that. It's pretty awesome. I highly recommend you watch the rest of it. Okay, so that's Einstein's first step, is weightlessness. Now, what's his second step? His second step is to think, well, if I let things fall, how do they fall? What's their motion? If I throw this, if I'm in literally empty space, there's no Earth, there's no sun, there's no other planets, and I throw this clicker, it's going to travel in a straight line. Does anyone doubt that? Wouldn't it be crazy if it started doing this? Right? It's just not the path of least resistance. If I throw it, it's going to travel in a perfectly straight line. That's what I expect it to do. But you know that if I throw it in this room, that's not what's going to happen. Right? If I throw it in this room, it's going to travel along an arc. I'm not going to do it because the tech guys are already mad at me. It's going to travel in an arc, and it's going to fall down and hit the Earth. So what Einstein realized is when things fall freely in the presence of something like the sun or the Earth, they don't follow straight paths. They follow curved paths. And he had this profound insight that matter and energy are curving space and time. They're creating curves in the actual shape around it. And the way we know that is by watching things fall. If we watch things fall, we can trace out their curved paths. What's happening with the International Space Station, it's not the fact that they don't feel gravity. They're not that far away, okay? What they're doing is they're falling. They're falling on a path that's always clearing the horizon, but they are at all times falling. Okay. The International Space Station, they're weightless for exactly the same reasons as the people we just watched in those videos, and that's because they're in free fall. So that's a pretty huge insight. Here, Einstein comes up with this tremendous revelation that space-time is curved due to matter and energy. The reason why the Earth orbits the sun on a circle is because there's a curved, circular, free-falling path around the sun. Now, it takes him many, many years to express it mathematically. It's a very difficult theory to write the math down, but the intuition is incredible. In this, again, not a cartoon, but a formal mathematical model, the physicist Andrew Hamilton has imagined you take the entire sun and you crush it to a black hole. Now, a black hole is proposed after Einstein in 1915 first writes down his greatest achievement, this general theory of relativity, this theory of curved spacetime. He gets a correspondence from Karl Schwarzschild, who's a German soldier on the Russian front. He's also an accomplished astronomer. And as I complain to my students who say they can't get any work done, I was like, Schwarzschild was calculating ballistic trajectories from the trenches. And then he's reading the proceedings of the Prussian Academy of Sciences, you know, as you do. And between calculating the ballistics trajectories and, you know, ducking for cover, he finds the solution, the mathematical solution. Einstein doesn't find it, Schwarzschild does, that we now call a black hole. It took until the 60s before it earned the name black hole. Now, what is a black hole? A black hole is a region of space and time where those curves are so strong that even light takes a curved path. Not only a curved path, but if light veers too close to the black hole, it will fall in. If light gets too close, it will never be able to escape. And that creates this shadow on the sky. You might think a black hole is a thing, like a crushed object, like a dense crush of matter, but it's not a thing at all. A black hole is really empty space. It's only pure gravity. It's only curves in space. If you were, we'll discuss this in a second, but if you were to get close to that shadow, there would be nothing there. It would not be like approaching the surface of a star or a planet. But it's a region where once you get there, no matter how fast or hard you try to escape, there's literally nothing you can do but fall inward. And that's why it creates this shadow. In this mathematical model, this self-illuminated Earth, what's happening is as it passes behind the black hole, you can see the bending of the path that the light takes. And that's why it looks so distorted. It's not that it's actually being distorted as you go behind it. It's just that the path of the light is being bent towards you. You know, there's this very good suggestion, if you ever do get into kind of like a space war, don't hide behind the black hole, okay? They can see you. So here's another beautiful mathematical model. It's a black hole. Pretend there were a black hole in that view we saw of the Milky Way between us and our perspective of the densest part of our galaxy. There isn't one so perfectly close. It would be fantastic if there was. But if we were a space explorer and we could go towards that black hole and we were orbiting around it, this is what we would see. We'd see the light from the galaxy bent around it as though it was a lens in the sky. And we'd see this big shadow. And if we didn't pay attention in astrophysics class, we wouldn't know better than to stay away, run. And if we foolishly crossed the horizon, right now, this astronaut technically is inside the black hole. And one thing I want you to notice is not only was there nothing there, they just crossed inside a shadow, but that the black hole's not dark on the inside, okay? They can see light from the galaxy fall in behind them and create, in fact, a very bright flash or burst of light. Black holes are dark from the outside, but not from the inside. Let's look closer at that inside perspective again. As you're falling towards the black hole, a lot of the light gets focused towards you because you're all crushing down to this point of extreme curvature. Everything's getting closer and closer together, and what it looks to you like is a big, bright flash of white light as the light falls behind you. I used to say it's like a near-death experience, only it's a total death experience. If you were to fall into a black hole about the mass of the sun, I think you would have about a microsecond before you were crushed to death in the singularity. After that, we don't know what happens. We don't know what happens on the inside. It's something extraordinary. It's a topic of research at many places, including a place like this. What happens at that singularity? To get blown out into a new universe? Is the black hole only 6 kilometers on the outside, but as big as an entire cosmos on the inside? These are all possibilities that we explore. But we're bound to the outside of the black hole. We don't get any of that good stuff, and probably that's just fine. But what can we see from the black hole? Now, here's where Einstein turns his attention. He gets this very fascinating correspondence from Schwarzschild, but he thinks these things will never form, and it's for good reason. I mean, how would you take the sun and crush it to a mere 6 kilometers across? It would fit in Waterloo, right? How could you possibly do that? He thinks, well, that just nature will not allow that to happen. Okay. And so it's a fascinating mathematical model, but nature just won't allow that to happen. He instead says the most important topic for him to turn his attention to in all of physics, all of science, is the existence of gravitational waves. And here's the idea. If something like the sun curves space and time, and if it were to be moving around or even orbiting with another heavy star, these curves in space and time must move and adjust with it. They must. And he was imagining almost like fish swirling in a pond, that it would create ripples and waves. And these waves are literally waves in the shape of space and time. If you were falling freely around the star, you would bob on the wave. How would you notice a wave had passed? You would move slightly, okay? You would move slightly because your free fall path would be changing, literally like a buoy bobbing on the ocean wave. And he's very confused about the existence of gravitational, this is not Einstein. Einstein's very confused about the existence of gravitational waves for a long time. He writes a paper saying they do not exist. He tells Schwarzschild he doesn't think they exist in a correspondence. Then he writes a paper within a year saying they do exist. Some years later, he writes another paper saying they do not exist. Between acceptance of the paper for publication and going to press, he sneaks in a completely different manuscript that says that they do. And one of his friends says, Einstein, you have to be really careful. Your famous name is going to be on these papers. And he says, my name is on plenty of wrong papers. You do not have to worry about that. This does not concern him at all. He's not risk averse, right? So by 1936, he's still saying he doesn't know if gravitational waves are real. And the community is arguing about it for decades. This is not easy stuff. Decades. 1968, 9, late 60s comes Joe Weber. Joe Weber is already a very accomplished, imaginative, great experimentalist who set out on a 10-year project practically single-handedly. He figures these theorists are still arguing about their, whether they exist or not, and their pen and paper, looking at their sheets of paper. I'm going to go out and have a look around, And he builds what is now known as a Weber bar. It's an aluminum bar. It's maybe 3,000 pounds. And it's kind of like a tuning fork. If a wave in the shape of space-time passes, it should pluck this Weber bar very, very, very slightly. And he measures the fluctual vibrations, like a tuning fork of this Weber bar. And by the late 1960s, at a general relativity conference that was pretty dull in these early days, Weber makes his announcement that he has detected gravitational waves. And you have to imagine, like, his pride, the pride to be the first, just the sheer gratification of discovery. At first, there's kind of pause or a moment, and then there's applause. People are beyond thrilled. They're excited. He's heralded. He's on the cover of magazines. He becomes, overnight, one of the most famous scientists alive. Very quickly, people are racing around trying to understand what Joe Weber is detecting. People like Stephen Hawking, Freeman Dyson, Martin Rees, the great minds of their generations are struggling to figure out what could make space-time ring like this. And they begin to consider possibilities, things like stars exploding. I'll explain to you soon why that's a sound. That would literally be the sound or the wave, okay, that you would hear, is one of the predictions. People start imagining maybe he's detecting supernova, stars exploding. There are things like pulsars, which are dead stars that didn't quite become black holes, that can create ripples in the fabric of space-time. What you were just listening to was the sound of those ripples. If they have even a little mountain on them, imagine a sphere with a little bump. It's like a paddle in the ocean. It would create these little waves, okay? And so there was a lot of suggestions of these possibilities that Joe was detecting. And pretty soon, there are Weber bars all over the world. They're in Japan, they're in Scotland, they're in Italy, and all over the States. NASA even put a different kind of instrument, but one of Joe's instruments on the moon. They were literally all over the place. And nobody detected a thing. The skies were dead quiet out there. Nobody but Joe. And so Joe becomes very cruelly ridiculed, unlike Einstein and Einstein's attitude about often being wrong and still exploring. The community did not look so favorably on Joe. And he spent the next 25 or 30 years defending his results. But nobody else ever cleanly, with a clean correspondence, defended Joe's detection. And so this field should have been dead. Okay? After that, there was such a negative, aggressive attitude against experimental pursuit of the existence of gravitational waves. People went after Joe so fiercely that they felt, look, I killed this field, it's dead, what are you doing trying to resurrect it? But there were people trying to resurrect it. In comes Ray Weiss, who at the time, let's call this the early 70s, is a young experimentalist at MIT, and he's just trying to understand the whole theory of relativity. He's asked to teach a class in relativity, and he admits, he doesn't really know anything about it. But he can't say that because he's trying to get tenure, And so he's teaching this class, and he says he's just one day ahead of the students, but the students aren't walking out. They're brainstorming all the time because he was thinking of ways to measure it. And what he hung on to in the whole class was this idea of the gravitational waves. And this was Ray's idea. He calls it a haiku. He said, imagine you suspend mirrors, those are mirrors at the ends there, down these little arms. If a gravitational wave passes, the mirrors will bob on the wave. And if you send a laser keeping track just of the location of those mirrors, you'll be able to tell if the mirrors have moved or not. It's just a simple idea. If the mirrors move, you're simply measuring their motion on the wave and thereby the wave itself. I liken it kind of to a musical instrument. If you think about how an electric guitar works, if you pluck a guitar string, it technically doesn't make a sound, the electric guitar string. It's really only after it's recorded by a whole amplifier system and plugged into an amplifier that you get the sound. And in a way, that's what LIGO's doing. Space-time is like a drum, and it's ringing. The mirrors are keeping track of that ringing, and they're plugging it literally into an amplifier system after it tracks the wave. You can listen to LIGO. This is the finished instrument. It takes them 30 years to build LIGO. Okay, so year 2000, they finally built it. It's a long and arduous story. There was a lot of opposition, and people like Kip Thorne, brilliant theorist, very influential astrophysicist, and the great experimentalist Ron Drever really pushed for it to be built. Barry Barish really pushed for it to be built. LIGO, the realization of this haiku of rays is an instrument that's 4 kilometers long. And down the 4-kilometer tunnels is the laser beam hitting a mirror at the far end. The mirrors are so perfectly reflective of the laser light. They're like 99.999% reflective. But they're completely transparent to optical light. If you look at them, they're invisible. It's really quite stunning. And there's 2 arms, just as in the original idea, each one 4 kilometers long. And there's 2 instruments, one on the coast in Louisiana and one in Washington state. And this is really important, both to make sure that you can kind of figure out the direction. It's kind of like having 2 ears, but also so that you cut down on false signals. Now, I'm going to tell you that the experimentalists actually listened to LIGO in the control room, and this is what it sounds like. Okay. That's an actual recording of LIGO back in the early days. It's just noise. It's vibrating all the time a little bit. If I walk past the tunnel, I can make it vibrate. Earthquakes in China have made the mirrors fall off. Winds from the Gulf Coast, traffic overhead, air traffic, the moon and the sun pulling on each other. All of these things cause the mirrors to vibrate a very little bit. So after this instrument was built in the year 2000, you didn't hear about it because it didn't detect anything. And Kip Thorne, one of the major proponents and advocates for this experiment, said he always knew that it was a 2-generation instrument. It wasn't until the year 2015 when they started to install the advanced component of the 2nd generation of machines that they were really holding their breath. You know, Ray said to me in August of 2015, Ray is in his 80s now, and he's there every day walking, well, not every day, but many days, walking the tunnels and working on the instrument. And I can't tell you how many times somebody said to me, we better ask Ray, you know, what's going on. Ray said to me in August, if we don't detect black holes, this thing is a failure. That's a pretty bold statement. So here we are, and we want to understand how can LIGO detect black holes. Now, when I say LIGO, it's like a sound. It's not only like a sound in the way that an electric guitar creates a sound out of the silent string. But if you were floating near those black holes, they literally can ring in the human auditory range. They ring space and time like mallets on a drum, and your eardrum would vibrate in response. Even in the absence of air, even though nobody can hear you scream, you could hear the gravitational wave ringing. This is a computer simulation of 2 black holes orbiting each other. What happens is as the black holes, like mallets on the drum, orbit each other, they get closer and closer and closer together. We're witnessing the final few orbits in this simulation, and these curves in space and time have been helpfully painted for us. They're not actually luminous. It would be completely dark, but it's painted for us. If you were floating nearby, those are the squeezing and stretching of space. It would ring your eardrum, and you would hear a sound. So let's listen to what they would sound like. At the end of the day, the 2 black holes collide and merge and create one bigger black hole that settles down and goes quiet. That's the theory. This, even this mathematical model took 25, 30 years to solve. It was such a hard problem, even on the computer. So here is a much simpler variant of that, an approximation of that. And what you're about to see is 2 black holes, just their orbits. In red is one black hole, in yellow is another black hole. They're the same size, and they're orbiting each other in circular orbits. And as they orbit, they lose energy. Just like you would if you were banging on a drum, you'd lose energy to the ringing of the drum. And they get closer and closer together as a result, and eventually they merge. And so we're listening to the final minute or so. Did that sound a little familiar? It's a little bit like the detection, right? It has a little whoop, chirp at the end. Here's another example of 2 black holes colliding. In this one of the black holes is 10 times heavier than the other, and so it's not moving as much. And I've also put them in crazier orbits, random orbits. And notice you can hear the difference. Okay? You can hear the difference between the 2 systems. And this whole system is actually moving around a lot. It gets quieter as it points away. It gets louder as it points towards us. orbiting. And eventually they're going to merge. Okay. And there's that classic chirp again. So as they get faster, the sound gets higher in pitch. And then they collide. And so these were predictions, all of which were motivated by LIGO's search. Things like this happened. LIGO had its own problems, not just those of the scorn of the community. One of the experiments is on the site of the previous plutonium separation facilities in Washington State. And because of that, there are guards that keep track of the plutonium, obviously keeping the area secure, and drive around in the middle of the night with a very poor knowledge of the local geography, like the fact that there's a cement tunnel 4 kilometers long. The actual tube itself is inside this tunnel. You can walk inside this tunnel, and I've walked the tunnel with Ray. Ray was one of the first people to walk the 4 kilometers several years ago, in many years, and he found wasp infestations and rats. And the tunnel that keeps the vacuum secure, the light has to pass through a region of a very strong vacuum. That tunnel is only 3 millimeters thin of this kind of stainless steel spooled structure. And stainless steel, it turns out, is not stainless to urine, which has chlorine in it. That's why your pools aren't made out of stainless steel. I mean, who knew these things? And so there were little tiny breaks in the vacuum and little leaks. So the vacuum was drawn in 1998 and has not been brought up to atmosphere since. It's the largest holes cumulatively in the Earth's atmosphere are the LIGO tubes. There is less stuff in those tubes than there are in regions of empty space. Had this security guard punctured the vacuum, it could have been fatal. It'd be like opening the door on the space shuttle, only the vacuum's on the inside, not the outside. Everyone was a little relieved he only broke his own arm, not one of the LIGO arms. And they also said if the vacuum had been broken, one of the head experimentalists told me we'd all go home. It would be over. This is a $1 billion experiment. There was another incident in Louisiana where hunters shot at the tunnels, and there was a little bit of a kerfuffle about that, whether that was intentional or accidental. But one of the experimentalists also said, we look so American to our European collaborators, you know? We have like car crashes, gun incidents, all we need is a hamburger incident, you know? So LIGO survives all of this. And here's some people, actually, I might as well throw this in. It's because it's quite stunning to see the equipment. At this time, LIGO began with Ray's haiku, Kip Thorne's insights, in Ron Drever's creative bursts, Barry Barish making it a fruition, but it went on for 50 years. By now, there's nearly 1,000 people in the experiment, and it's an international collaboration with over 100 institutions, and these are extremely sophisticated systems. They're called cartridges. They have these beer cartons at the end of the tunnels where they drop the mirrors and pull them in and out. It's really quite spectacular to watch them working. So let's get to 2015. August 2015, Ray says, if we don't detect black holes, this thing is a failure. All the experimentalists, meanwhile, are telling me there's no way we're going to detect black holes. It's years away. Years. We're not going to get anything for years. It's 2015, and the time then was only just to test the instrument. By September, the experimentalists are nearly ready, but they're not quite ready. They have to postpone their science runs because some of the things they just can't bring online just yet. So it's September 14th. It's the middle of the night, and they're messing with the instrument. Messing with the instrument can mean many things. They're intentionally making noise to measure the noise, to see how good it's doing. And around the middle of the night, in Louisiana, it's almost 5 a.m. They're exhausted. They're fed up. They decide just to stop for the night. They put their tools down. They go home. Same thing happens in Hafer, Washington, about the same time. It's been 100 years since Einstein first proposed the existence of gravitational waves. And within an hour of them putting their tools down, probably some of them still making their way home, a signal strikes. It's recorded beautifully at the Louisiana site, coming from the southern sky. It travels across the continent and rings the machine in Washington. And what they recorded, once they reconstructed the sound, was the collision of two black holes 1.3 billion years ago, plus or minus a few hundred million years, you know. It's not that precise. Each one was about 30 times the mass of the sun. One was maybe 29, one was maybe 35 times the mass of the sun. We caught the final, this is again not a cartoon, it's a computer simulation of the event. It's also not an observation because we can't see it. We caught the final few orbits of these two black holes around each other. This is drastically slowed down. The black holes were traveling very near the speed of light, and orbiting as close as a couple of hundred of kilometers apart. And those 4 or so orbits that they executed near the end took 1/5 of a second. Okay? And then they settled down to make one final black hole. So let's listen again to what it sounded like now that we've been through that long journey. Here we are again. First, it's going to play twice at the actual frequency, which is in the human auditory range. The LIGO happens to be sensitive to the same frequency range as the piano. And then we're going to play it again, increased in pitch, which is easier to hear with the human ear. When Ray woke up at 8:30 that morning and checked the logs, as he always does, out of habit, he saw a freeze on all action at the site and a candidate in the log, and he thought, what the hell is this? You know? And by then, Europe was awake. Everyone's on the phones. Nobody can believe it. They spend months practically accusing each other of faking the signal, investigating any possible mistake, any possible error, any possible way it could be hacked, any other possibility other than the one that they firmly concluded that it is. I got a note from the director of LIGO, David Wrightsey, a month or two later, and the subject line was just confidential communication from LIGO. My heart stopped. You know, I thought, oh my God, this is it. Since then, there have been more detections. This is another detection that happened on Boxing Day, December 26th of the same year, of 2016. I guess it would be 2015, rather. This is one bigger black hole, about 15 times the mass of the sun, and a smaller black hole. And that, as it says here, that collision took about 17 milliseconds. And now, again, the same visual on the collision, but just from a different perspective. And while that wasn't as loud an event, it was still beautifully recorded by both instruments, and we're going to listen to that one in a second, too. Let's hear it. Okay, so this is December 26, 2015, compared to the September event. Notice the smaller one's higher, and the bigger one's lower, bigger system. New ringtones, everyone. Quite remarkably, what they detected, let's just talk about the first event again. What they measured was swinging of their mirrors by less than 1/10,000th the width of a proton over 4 kilometers. That's what they measured. That's why they didn't detect anything in the year 2000, because they need to get even more sensitive. In the year 2000, that same system, those black holes were orbiting each other for those 15 years, for sure. They were just further apart and not quite as loud. It wasn't until the final 1/5 of a second that it was loud enough for us to record with those machines. And when they did record it, what they recorded was the single most energetic event since the Big Bang. More power came out of that collision than all the power in all the light of all the stars in the observable universe combined. And none of it came out as light. It all came out as gravitational waves. So this is this completely new era that we're on, where we're able to detect things that are entirely dark. And we have this opportunity to really probe the universe for the first time in this completely original way, this completely new way. And so just to conclude, I don't think it's a spoiler. I was going to read something from the book. I'm going to read the last few lines. I hope you don't mind. Again, I don't think it's a spoiler. I can tell you what happens. They detect gravitational waves. Okay, so this is also, by the way, the Hubble Deep Field. This is another example of galaxies that we see with the Hubble Space Telescope. This is a tiny region of the sky that's less than the size of the moon, and there's many thousands, tens of thousands of galaxies in this tiny piece of the sky. There will be press releases, scientific papers will be published, news articles will abound. There will be documents, reports, and carefully kept records kept. We'll continue to send a portrait of our best selves into space, a declaration that we were here, that we strove for understanding, that we often failed and occasionally succeeded. We heard black holes collide. We'll point to where the sound might have come from to the best of our abilities, a swatch of space from an earlier epoch. Somewhere in the southern sky, pulling away from us with the expansion of the universe, the big black hole will roll along its own galaxy, dark and quiet, until something wanders past, an errant dust cloud or another star. After a few billion years, the host galaxy might collide with a neighbor, tossing the black hole around, maybe toward a supermassive black hole in a growing galactic center. Our star will die. The Milky Way will blend with Andromeda. The record of this discovery, along with the wreckage of our solar system, will eventually fall into black holes, as will everything else in the cosmos, the expanding space silent, and all the black holes will evaporate into oblivion near the end of time. Thank you. Any questions?
Wow. Have online questions too. Fantastic. We will open the floor to questions. I'm going to go read the book.
Right now.
Aiden, you're up.
How do supernova affect LIGO?
So originally, when they designed some of the very specific specs for the instrument, they had supernova in mind as best candidates. And that changed over time because the understanding of the underlying science changed over time. But we thought that supernova, if they explode particularly in an odd kind of shaped way, could be very loud sources and very populous sources. But it turns out we haven't detected any supernova yet. And that might just be where LIGO is doing best, is at lower notes, and the supernova would be at higher notes. But fingers crossed, in the future, we will one day record this very sudden sound of a supernova exploding.
How would you guess it'd sound?
Well, it's a great question. We theoretically model the sound, just as though if I had never heard somebody play a drum, but they told me the motions they were going to make, the size and shape of the mallets, I could reconstruct or predict the sound that it would make. And it's very similar to that. We're not great at predicting supernova sounds is the problem. There's some excellent work done on it. It's just that it turns out that even the theory seems to be saying they're quieter than we originally anticipated.
Okay.
Thanks. You accept that? That's cool. Okay.
Great stuff. Let's go to an online question, and there is a few of them. What part of the EM spectrum is revealing the jets that you mentioned emanating from a black hole?
Those, I think, are in the radio. And the jets, it depends. There's lots of jet systems. We also think smaller black holes the size of stars that have collapsed, not billions or millions of times the mass of the sun, but the size of stars that collapse can create jets as well, just out of the debris of neighboring stars and twisting up magnetic fields. And we often see those in radio. But we can see them sometimes in gamma rays and X-rays because, so radio waves are lower energy waves of light, but the gamma rays and the X-rays are very high energy. And sometimes these black holes are spewing charged particles out along magnetic field lines at such incredibly relativistic velocities, which means very near the speed of light, that they're emanating radiation at the absolute highest energies, which would be gamma rays and beyond.
Excellent, thank you. In the theater.
My question is, there was an assumption probably that the waves will come in low frequencies. Because of that, the structure measured the sound that we can hear. Why is that frequency band was explored?
It's just a coincidence based on the size of the systems. If you have bigger systems, they make lower notes, which is what you expect. A bigger drum ringing makes a lower note than something smaller. And so there's experiments that are proposed for space that could detect things like supermassive black holes colliding, and they would be very big systems. But people always think black holes are enormous, or these enormous. Black holes are actually small. That's the whole point, is that they're small. These black holes that were about 30 times the mass of the sun are only a couple of 100 kilometers across. And it's the size of the system and how quickly they're orbiting each other that sets the frequency at which they vibrate space and time. So bigger systems, lower notes, smaller systems, higher notes. And that's why at the end they get higher, because they're going faster and closer. So they're getting smaller.
Great, let's go in the theater again. Can you reach that? Good work.
What will happen if Earth got sucked up in a black hole?
Yeah. It would be bad. There's really not a good outcome to that. Luckily, there aren't any black holes nearby, so we're pretty safe. I'd be much more worried about impending votes in Congress or something like that. But I'm going to give you a little bit more, because I think it's a cool question. How about just you fell into a black hole? What happens is you get kind of stretched out. Your feet and your head get stretched out because the gravitational pull is stronger at your feet than at your head. You get what some people call spaghettified, and it's not a very pleasant experience. And then you find your way towards the singularity, but maybe there's some way in which you get thrown out into a new Big Bang again. It's a definite mystery.
Great. What's your name? Max. Thank you, Max. Great question. All right. I'll go back online. And so and you addressed this in the talk a little bit. What do you think is more impressive, that LIGO detected gravity waves or that LIGO was built at all?
Yeah. One is impressive, one is lucky. I think it's incredibly impressive, which is why the book really became about the campaign to build LIGO, not about its success. I actually printed a copy of the book on September 14th. One for Kip and one for Ray, not knowing that the instrument had just been ringing. And I sent them drafts of the book, and Ray was, I could tell, really edgy and uncomfortable. And he's like, what are you going to do if there's a discovery? Are you going to rewrite the book? And I tried to explain that I could never have captured that sense of tension, the genuine tension of working on something that you don't know will succeed for 50 years of your life, and aiming for the centenary, 100 years since Einstein. And it was really about that, not about the success for me. But the success itself was, I think, one of the greatest moments for a lot of us who were watching. And that part of that was just nature being generous. We really didn't know how many black hole sources would be out there, and we didn't know how long we'd have to wait.
All right, let's finish up with one more question, and apologies if this is predictive, but I can't help myself. What new discovery are you most hoping the detection of gravitational waves will help us make?
Yeah, when I was a student at MIT and thinking about black hole astrophysics or gravity or gravitation, and I would listen to Kip Thorne, who was just an incredibly inspiring, brilliant scientist. And Kip would often talk about the unknown, what we might discover that we haven't even thought of yet. And that was always the most thrilling. I think that's what I really hope, is like when Galileo looked at the sunspots, it's an incredible achievement, but he couldn't possibly have foreseen galaxies and quasars and the Big Bang. And so maybe there's stuff out there we just haven't even thought of yet. Yeah.
Ladies and gentlemen, Dr. Janna Levin.